Your 10-year-old just asked you to explain how Netflix knows what they'll like, or how Siri learned to understand voices. You freeze. You know it's machine learning, but how do you break it down without losing them in the jargon? Here's the thing. There are really just two fundamental ways machines learn from data, and once you understand that split, the whole world of AI starts making sense. My name is Lakshmi Venkataraman, and I specialize in helping families navigate exactly this kind of conversation. Welcome to the STEM Lab podcast. Quick heads up before we dive in. Everything you're about to hear, the research, the examples, the advice, that's all been written and verified by real human experts. The voice delivering it, though, that's AI generated. We think it's a good trade-off for getting this information to you quickly and consistently, but we wanted you to know. Now, if you're a regular here, if you've been listening for a while, thank you. I don't take that for granted. If you're new, welcome. I'm glad you found us. We drop new episodes every Monday, Wednesday, and Friday, covering everything from coding to robotics to AI education. Always practical, always parent-focused. Today, we're talking about supervised versus unsupervised learning, and I promise by the end of this, you'll have a way to explain it to your kid that actually makes sense. Let's go. If you're helping your child navigate the world of AI and machine learning, you've likely encountered the terms supervised and unsupervised learning, and you may be wondering how to explain these foundational concepts without drowning in technical jargon. These two approaches form the backbone of how machines learn from data, and understanding the difference helps your child grasp not just what AI does, but how it actually thinks. This distinction becomes especially important as your learner moves from visual block-based coding into text-based languages, where they'll implement these algorithms themselves. Let me walk you through this in a way that connects classroom rigor with kitchen table clarity. So, what exactly is supervised versus unsupervised learning for kids? Supervised learning is the process where a machine learns from labeled examples. Think of it as learning with an answer key. You show the algorithm input data, like pictures of cats and dogs, along with the correct labels saying cat or dog, and it learns to recognize patterns so it can correctly label new images it's never seen before. The supervision comes from those pre-labeled training examples guiding the learning process. Unsupervised learning, by contrast, works without labels. The algorithm receives raw data and must find patterns, groupings, or structures on its own. Imagine dumping a box of mixed Lego bricks on the table and asking your child to sort them into piles that make sense by color, size, or shape without telling them which sorting method to use. The machine identifies hidden relationships in data without being told what's right. This distinction matters because different real-world problems require different approaches. Supervised learning excels when you have clear categories and labeled training data. We're talking spam detection, medical diagnosis, handwriting recognition. Unsupervised learning shines when you're exploring data to discover unknown patterns like customer segmentation, anomaly detection, recommendation systems. Both approaches appear in age-appropriate AI learning platforms, though supervised learning typically comes first in progressive STEM learning paths because the concept of learning from examples is more intuitive for young learners. Now let's talk about how supervised learning actually works. I've watched hundreds of sixth graders struggle with this exact misconception. They think the machine memorizes examples like flashcards, but supervised learning is about pattern recognition, not rote memorization. During the training phase, the algorithm receives a training data set composed of input-output pairs. For instance, if you're teaching a model to identify handwritten digits, the input might be a 28 by 28 pixel grid showing a handwritten 3, and the output would be the label 3. The algorithm examines thousands of these pairs, adjusting its internal parameters, what we call weights, to minimize the difference between its predictions and the actual labels. This process involves making a prediction based on current parameter values, calculating error by comparing the prediction to the true label, adjusting parameters to reduce that error, and repeating across thousands of examples until accuracy plateaus. This iterative refinement is called training, and it's why machine learning requires substantial computational power and time. Something like a Raspberry Pi 5 starter kit, check the link below to see the current price, provides enough processing capability for simple supervised learning models using Scratch ML extensions or beginner Python libraries, though more complex models will need cloud-based platforms. Once trained, you evaluate the model's performance using a test dataset, data it has never encountered during training. This distinction is crucial. If you only tested the model on training data, you'd measure memorization, not genuine learning. The test set reveals whether the model has learned generalizable patterns or just overfit to the training examples. This scaffolds the scientific method beautifully. Hypothesis, that's your model structure, experimentation, that's training, and validation, that's testing, mirror the inquiry process your child practices in well-designed science investigations. When it comes to real-world implementation for kids, platforms like Scratch's ML extension and Google's Teachable Machine make supervised learning accessible to elementary and middle school learners. Your child can train an image classifier to distinguish between hand gestures, facial expressions, or household objects in under 10 minutes, using their webcam as the data source and visual blocks instead of code. The AIY Vision Kit, check the link below to see the current price, takes this further, allowing kids to train on-device models that run without internet connectivity, a critical consideration for screen time management and data privacy. It operates on Raspberry Pi hardware, not included, and uses TensorFlow Lite, the same framework deployed in professional applications. For text-based learners ready for Python, the scikit-learn library provides supervised learning algorithms with surprisingly simple syntax. A functional decision tree classifier can be implemented in about 15 lines of code, appropriate for ages 12 and up who've completed foundational Python skill milestones. Moving on to how unsupervised learning works, unsupervised learning operates without the safety net of labeled examples, which makes it conceptually trickier for young learners, but incredibly powerful for real-world exploration. Let's start with clustering algorithms. Clustering groups data points based on similarity. The k-means algorithm, one of the most common clustering methods, works like this. You choose the number of groups, that's k, you want to find. You place k center points randomly in your data space. You assign each data point to its nearest center. You move each center to the average position of its assigned points. Then you repeat those last two steps until centers stop moving. I use a physical activity to teach this. Give students sticky notes with different numbers written on them spread across the classroom floor. Ask them to form 3 groups where notes within each group have similar values. They'll naturally gravitate toward low, medium, and high number zones. That's clustering. For kids, clustering appears in activities like sorting images by visual similarity without being told categories, grouping songs by musical characteristics like tempo, mood, or genre based on audio features, or organizing survey responses to discover customer segments. The Little Bits Rule Your Room kit, check the link below to see the current price, includes sensor-based data collection that can feed into simple clustering activities, though it requires integration with Python scripts for actual unsupervised learning. It's not out-of-box ML. Another unsupervised technique is dimensionality reduction. This technique simplifies complex data by finding the most important features. Imagine describing a person's face. Instead of storing millions of pixel values, dimensionality reduction identifies that eye distance, nose length, and face width capture most of the variation between faces. For middle schoolers exploring AI concepts, this parallels summarizing a book chapter. You extract the key points while preserving the essential meaning. Practically, it makes large data sets manageable and visualizable, preparing students for the data-heavy reality of machine learning careers. Unsupervised algorithms can also do pattern discovery and anomaly detection. They can identify unusual data points that don't fit established patterns, a critical capability in cybersecurity, quality control, and fraud detection. Your child's credit card company uses this when it flags suspicious purchases that deviate from your typical spending behavior. This concept translates beautifully into science fair projects. Collect environmental data, temperature, humidity, air quality, over several weeks, then use unsupervised learning to detect anomalous readings that might indicate measurement errors or genuine environmental events. So, why does understanding supervised versus unsupervised learning for kids actually matter? The distinction between supervised and unsupervised learning isn't academic trivia. It's a conceptual framework that shapes how your learner approaches computational problem solving throughout their STEM education. First, it's preparing them for industry-standard workflows. Professional data scientists spend significant time deciding which approach fits their problem. Does available data include labels? If not, can labels be acquired, or should unsupervised methods be deployed? Your middle schooler working through this decision-making process develops the same analytical framework used in research labs and tech companies. Machine learning career paths increasingly require understanding these fundamentals by undergraduate internship applications. Students who've implemented both supervised and unsupervised models, even in Scratch or Python, demonstrate practical AI literacy that stands out on high school resumes and college applications. This also connects directly to next-generation science standards. The NGSS emphasizes using computational thinking to model complex systems and analyzing data to identify patterns. Both supervised and unsupervised learning directly address these standards, particularly in middle school life science, that's analyzing genetic data, earth science, climate pattern recognition, and physical science, classifying particle collision events. When your child builds a supervised classifier to identify plant species from leaf images, they're hitting cross-cutting concepts around patterns, cause and effect, and systems modeling. When they use clustering to group similar weather patterns, they're practicing data analysis skills that transfer across STEM disciplines. There's also the benefit of scaffolding from concrete to abstract. Supervised learning typically comes first in learning progressions because the feedback loop is intuitive. I taught it using examples, now it can recognize new examples. This builds confidence before introducing unsupervised learning's ambiguity, where correct answers are less clear-cut. This progression mirrors cognitive development. Younger learners, ages 8 to 10, grasp supervised learning through tools like Scratch ML extensions, while unsupervised concepts typically land better around ages 11 to 13, when abstract reasoning strengthens. Let me break down the types and variations you'll encounter. The supervised versus unsupervised learning framework actually encompasses several subtypes, each with distinct characteristics and applications. Within supervised learning, there's classification, which assigns data to discrete categories: spam or not spam, cat, dog, or bird. This is the most common type in educational kits because results are easy to validate. There's regression, which predicts continuous numerical values like house prices, temperature forecasts, crop yields. It appears less frequently in kids' AI kits, but becomes important in science fair projects involving measurement and prediction. And there's time series prediction, which forecasts future values based on historical sequences. That's relevant for weather modeling, stock simulation in educational contexts, and sensor data analysis. Within unsupervised learning, clustering groups similar items together. We covered K-means, but hierarchical clustering and DB-scan offer different approaches with varying complexity levels. Association rule learning discovers relationships between variables. Customers who buy X often buy Y. This appears in recommendation system projects appropriate for ages 12 and up. Generative models learn to create new data similar to training examples. Recent generative AI tools, image creation, text generation, use unsupervised and semi-supervised techniques, though understanding these requires solid foundational knowledge first. There's also semi-supervised and reinforcement learning. Semi-supervised learning bridges both worlds, using a small labeled dataset plus a large unlabeled one. That's practical for real-world scenarios where labeling is expensive or time-consuming. Reinforcement learning is technically a separate category where agents learn through trial, error, and rewards. It's conceptually distinct from supervised and unsupervised approaches, though many educational resources group them together. If your child is interested in game-playing AI or robotics navigation, that's reinforcement learning territory. Now let's talk about the lab specs for at-home AI learning. Setting up for supervised versus unsupervised learning for kids requires consideration of technical requirements that vary dramatically by platform and skill level. For entry level, that's ages 8 to 10 doing block-based coding, you need any laptop or desktop manufactured within the last 5 years. Chromebooks work with Scratch ML extensions. You'll want 4 GB of RAM minimum, 8 GB recommended, and a webcam, either built-in or USB, for image and video training data. No GPU required. Standard laptop battery or outlet power works fine. And you'll need internet for most block-based platforms like Teachable Machine or Scratch ML. Models typically run in your browser. For intermediate level, ages 11 to 13 transitioning to Python, you need Windows 10 or 11, Mac OS 10.14 or later, or Ubuntu 20.04 or later. 8 GB of RAM minimum. Processor should be an Intel i5, AMD Ryzen 5 or better. You'll want 20 GB of free storage for Python libraries and datasets. Internet is needed for library installation and cloud training, but offline execution is possible after setup. You can optionally use something like the Raspberry Pi 5 starter kit, check the link below to see the current price, for dedicated ML projects, but it requires a separate keyboard, mouse, and monitor. For advanced level, ages 14 and up working on complex models, it's the same as intermediate, but 16 GB of RAM is recommended. A GPU is optional, but accelerates training significantly. NVIDIA cards with CUDA support are preferred. Cloud alternatives like Google Colab's free tier or Kaggle notebooks eliminate hardware requirements for computation-intensive projects. On the software side, for block-based platforms, you've got Scratch 3.0 with ML extensions, Google Teachable Machine, and MIT App Inventor with image recognition components, all browser-based, all free, no installation, no version conflicts, works across operating systems. For Python-based tools, you're looking at Python 3.8 through 3.12. Avoid 3.13 until library compatibility improves. You'll use libraries like scikit-learn for supervised and unsupervised learning, pandas for data handling, matplotlib for visualization. Development environments include Thonny, which is beginner-friendly, VS Code for a professional setup, or Jupyter Notebooks for exploratory work. Installation requires 2 to 3 hours for first-time setup, and there's a package management learning curve. When it comes to expandability and progressive learning, look for platforms that support a skill ladder progression. Visual model training with something like Teachable Machine for ages 8 to 10, block-based ML coding with Scratch extensions for ages 9 to 11, Python with high-level libraries like scikit-learn for ages 12 to 14, deep learning frameworks like TensorFlow or PyTorch for ages 15 and up. Avoid isolated toys that don't connect to industry-standard tools. The value proposition lies in building transferable skills, not one-off activities. The NVIDIA Jetson Nano Developer Kit, check the link below to see the current price, represents the high end of this progression. It's essentially a dedicated AI computer that runs full Linux, Python, and professional frameworks, appropriate for serious high school learners aiming toward computer science programs. Let me answer some frequently asked questions. What age is appropriate to start teaching supervised versus unsupervised learning for kids? Children as young as 8 can grasp supervised learning concepts through visual, example-based platforms like Google Teachable Machine, where they train image classifiers by showing examples and immediately testing results. The concrete cause and effect relationship, I show cat pictures, it learns cats, aligns with their developmental stage. Unsupervised learning typically makes more sense around ages 11 to 12 when abstract thinking strengthens and kids can understand finding patterns without knowing what you're looking for. That said, you can introduce clustering through physical sorting activities with younger children. The formal AI terminology can wait until they're implementing it computationally. The key milestone is whether your child can articulate why they chose their groupings and what patterns they noticed. Do kids need to learn supervised learning before unsupervised learning? While not strictly required, supervised learning provides a more intuitive entry point because the feedback mechanism is explicit. The algorithm knows when it's wrong and adjusts accordingly. This creates a clear mental model of how machines learn from mistakes. Unsupervised learning's ambiguity, no right answers, multiple valid groupings, can be frustrating without that foundation. In practice, most AI learning kits and curricula introduce supervised classification first, then branch into unsupervised methods once the broader concept of learning from data has solidified. The exception is physical sorting activities with young children, where clustering is tangible and doesn't require understanding the underlying algorithms. For computational implementations, stick with the supervised first progression unless your child specifically gravitates toward open-ended exploration over goal-directed tasks. Can kids implement supervised and unsupervised learning without expensive AI kits? Absolutely. The most accessible and powerful tools are free software platforms that run on standard computers you likely already own. Google Teachable Machine, Scratch ML extensions, and Python with scikit-learn cost nothing beyond your existing hardware. You don't need specialized robotics kits, though products like the AYI Vision Kit, around $90, check the link below to see the current price, or dedicated AI platforms add tangible, device-based learning experiences that some kids find more engaging than screen-only coding. The real investment is time, not money. Downloading Python libraries, working through tutorials, debugging code, and collecting training data require patience and parental involvement, especially during the first few projects. Cloud platforms like Google Colab eliminate even hardware requirements for more advanced deep learning experimentation. Save your budget for robotics kits or 3D printers that have genuine hardware requirements. AI learning is largely a software journey. How do supervised and unsupervised learning connect to other STEM skills like robotics or 3D printing? Machine learning integrates with robotics through computer vision, supervised learning for object recognition and sensor data analysis, unsupervised anomaly detection in robot behavior. A robot navigating obstacles might use supervised learning to identify objects from camera feeds, then apply those classifications to navigation decisions. The Arduino programming skills your child develops for motor control and sensor interfacing combine with Python ML libraries to create intelligent robotic behaviors. That integration typically happens around ages 13 to 15 after foundational competency in both domains. For 3D printing, machine learning appears in quality control, detecting failed prints from camera images, generative design, algorithms that create optimized structures, and parametric modeling, learning what design parameters produce desired results. These applications are advanced, but the conceptual groundwork laid through supervised versus unsupervised learning projects makes them accessible to high school students pursuing engineering pathways. Let me wrap up with building long-term ML competency. The supervised versus unsupervised learning distinction provides your child with a mental framework that organizes not just their current AI projects, but their entire computational problem-solving approach as they progress through middle school, high school, and potentially into undergraduate STEM coursework. When you frame these concepts as skill-building investments rather than isolated activities, you're setting up a learning trajectory that mirrors professional data science workflows. Your 11-year-old training a Scratch ML model to recognize hand gestures is practicing the same problem decomposition, data collection, model evaluation, and iteration process that a machine learning engineer applies to medical image analysis or natural language processing. The technical depth increases from visual blocks to Python to TensorFlow, but the conceptual foundation remains constant. That's why understanding supervised versus unsupervised learning for kids matters. It's not about the specific algorithm they implement today, but about building the analytical architecture they'll use for the next decade of computational learning. Start with concrete, quick feedback supervised learning projects that build confidence. Introduce unsupervised clustering when your child shows readiness for ambiguity and open-ended exploration. Connect both to their other interests: sports statistics, music analysis, environmental data, creative projects. The most effective AI learning happens when algorithms become tools for answering questions your child genuinely cares about, not abstract exercises in a vacuum. And remember, you don't need to be an AI expert yourself. Your role is creating the infrastructure, providing hardware access, allocating time, connecting them with resources while they build the expertise. These skills compound rapidly with practice, and 6 months from now, you may find yourself asking them to explain the latest model they've trained. That wraps up this episode of the STEM Lab podcast. Thanks for listening. We're back every Monday, Wednesday, and Friday with new episodes. So if you enjoyed this one, hit subscribe or follow, whatever your app calls it, so you don't miss the next one. And hey, if you have a minute, leaving us a 5-star rating and a quick review actually makes a huge difference. It's how other parents and educators find the show, and it helps us reach people who need exactly this kind of breakdown. Seriously, it takes 30 seconds, and it helps more than you think. All right, I'll catch you in the next episode.